Chapter 3, Einstein. This is the most important result, obtained in connection with the theory of gravitation since Newton's day. Einstein's reasoning is the result of one of the highest achievements of human thought. These words were uttered by Sir J. Thomson, the president of the Royal Society, at a meeting of that body held on November 6, 1919, to discuss the results of the eclipse expedition. Einstein and other Newton, and this from the lips of J. Thomson, England's most illustrious physicist. If ever men weighed words carefully, is this Cambridge professor, whose own researches have assured him immortality for all time. What has this Albert Einstein done to merit such extraordinary praise, with the world in turmoil, with classes and races in a death struggle, with millions suffering and starving? Why do we find time to turn our attention to this jewel? His ideas have no bearing on Europe's calamity. They will not add 1 bushel of wheat to starving populations. The answer is not hard to find. Men come and men go, but the mystery of the universe remains. It is Einstein's glory to have given us a deeper insight into the universe. Our scientists are Huxley's agnostics. They do not deny activities beyond our planet. They merely center their attention on the noble on this earth. Our philosophers, on the other hand, go far afield. Some of them soar so high that, like one poet's opinion of Shelley, the bubble bursts Einstein. Using the tools of the scientist, the experimentalist builded a skyscraper, which ultimately reached the philosophical school. His rail is the rail of alcohol in causing water and ether. The anesthetic to mix ether and water will mix no better than oil and water. Without the presence of alcohol, in its presence a uniform mixture is obtained. Einstein prophesied that a ray of light passing near the sun would be pulled out of its course due to the action of gravity. He went even further. He predicted how much out of its course the ray would be deflected. This prediction was based on a theory of gravitation which Einstein had developed in great mathematical detail. The object of the British eclipse expedition was either to prove or disprove Einstein's assumption. Einstein's prophecy was fulfilled almost to the letter. Since Einstein's theory of gravitation is intimately associated with certain revolutionary ideas concerning time and space and, therefore, with fundamentals of the universe, the net result of the expedition was to strengthen our belief in the validity of his new view of the universe. It is our intention in the following pages to discuss the expedition and the larger aspects of Einstein's theory that follow from it. But before we do so, we must have a clear idea of our solar system. In the center of our system is the sun, a flaming mass of fire, much bigger than our own Earth and very, very far away. The sun has its family of 8 planets, of which the Earth is one, which travel around the sun, and around some of the planets there travel satellites or moons. The Earth has such a satellite, the moon. Now we have good reasons for believing that every star which twinkles in the sky is a sun comparable to our own, having also its own planets and its own moons. These stars or suns are so much further away from us than our own sun that but a speck of their light reaches us, and then only at night, when, as the poet would say, our sun has gone to its resting place. The distances between bodies in the solar system is so immense that, like the number of dollars spent in the Great War, the number of miles conveys little or no impression. But picture yourself in an express train going at the average rate of 30 miles an hour. If you start from New York and travel continuously, you would reach San Francisco in 4 days. If you could continue your journey around the earth at the same rate, you would complete it in 35 days. If now you could travel into space and to the moon, still with the same velocity, you would reach it in 350 days. Having reached the moon, you could circumscribe it with the same express train in 8 days as compared to the 35 days it would take you to circumscribe the earth. If instead of traveling to the moon, you would book your passage for the sun, you, or rather your descendants, would get there in 350 years, and it would then take them 10 additional years to travel around the sun. Immense as these distances are, they are small as compared to the distances that separate us from the stars. It takes light which, instead of traveling 30 miles an hour, travels 186,000 miles a second, about 8 minutes to get to us from the sun, and a little over 4 years to reach us from the nearest star. The light from some of the other stars do not reach us for several hundred years. Now to return to an infinitesimal part of the universe, our solar system. We have seen that the earth travels around the sun and the moon around the earth. At some time in the course of these revolutions, the moon must come directly between the earth and the sun. Then we get the eclipse of the sun, as the moon is smaller than the earth. Only a portion of the earth's surface will be cut off from the sun's rays. That portion which is so cut off suffers a total eclipse. This explains why the eclipse of May 1919, which was a total one for Brazil, was but a partial one for us. Einstein claimed that a ray of light from one of the stars, if passing near enough to the surface of the sun, would be appreciably deflected from its course, and he calculated the exact amount of this deflection. To begin with, why should Einstein suppose that the path of a ray of light would be affected by the sun? Newton's law of gravitation made it clear that bodies which have mass attract one another. If light has mass, and very recent work tends to show that it has, there is no reason why light should not be attracted by the sun or any other planetary body. The question that agitated scientists was not so much whether a ray of light would be deviated from its path, but to what extent this deviation would take place. Would Einstein's figures be confirmed? Of the bodies within our solar system, the sun is by far the largest, and therefore it would exert a far greater pull than any of the planets on light rays coming from the stars. Under ordinary conditions, however, the sun itself shines with such brilliancy that objects around it, including rays of light passing near its surface, are wholly dimmed. Hence the necessity of putting our theory to the test. Only when the moon covers up the sun, when there is a total eclipse of the sun, Imagine a star so selected that as its light comes to us, the ray just grazes the sun. If the path of the ray is straightest, the sun has no influence on it. Then the path can be represented by the line of B. If, however, the sun does exert a gravitational pull, then its real path will be a B, and to an observer on the Earth the star will have appeared to shift from a to a. Do photographs of stars around the sun were to be taken during the eclipse, and these photographs compared with others of the same region taken at night with the sun absent. Any apparent shifting of the stars could be determined by measuring the distances between the stars, as shown on the photographic plates. According to Newton's assumption, light consists of corpuscles, or minute particles, emitted from the source of light. If this be true, these particles, having mass, should be affected by the gravitational pull of the sun. If we apply Newton's theory of gravitation and make use of his formula, it can be shown that such a gravitational pull would displace the ray of light by an average amount equal to 0.75 seconds of angular distance. On the other hand, where light is regarded as waves set in motion in ether of space, the wave theory of light, and where weight is denied light altogether, no deviation need be expected. Finally, there is a third alternative. Einstein's light, says Einstein, has mass and therefore probably weight. Mass is the matter light contains. Weight represents pull by gravity. Light rays will be attracted by the sun, but according to Einstein's theory of gravitation, the sun's gravitational pull will displace the rays by an average amount equal to 1.75 seconds of angular distance. That science is highly international, despite many recent examples to the contrary, is evidenced by this British eclipse expedition. Here was a theory propounded by one who had accepted a chair of physics in the University of Berlin, and across the English Channel were Germany's mortal enemies, making elaborate preparations to test the validity of the Berlin professor's theory. The British Astronomical Society began to plan the eclipse expedition even before the outbreak of the Great War. During the years that followed, despite the destinies of nations which hung on threads from day to day, despite the darkest hours in the history of the British people, our English astronomers continued to give attention to the details of the proposed expedition. When the day of the eclipse came, all was in readiness. One expedition under Dr. Crommelin was sent to Sobral, Brazil, another under Professor Eddington to Principe, an island off the west coast of Africa. In both these places a total eclipse was anticipated. The eclipse occurred on May 29, 1919. It lasted for 6 to 8 minutes. Some 15 photographs with an average exposure of 5 to 6 seconds were taken. 2 months later, another series of photographs of the same region were taken, but this time the sun was no longer in the midst of these stars. The photographs were brought to the famous Greenwich Observatory near London, and the astronomers and mathematicians began their laborious measurements and calculations. On November 6, at the meeting of the Royal Society, The result was announced. The Sobral expedition reported 1.98, the Principe expedition 1.62. The average was 1.8. Einstein had predicted 1.75. Newton might have predicted 0.75, and the orthodox scientist would have predicted 0. There could now no longer be any question as to which of the three theories rested on a sure foundation. To quote Sir Frank Dyson, the astronomer royal, after a careful study of the plates, I am prepared to say that there can be no doubt that they confirm Einstein's prediction. A very definite result has been obtained, that light is deflected in accordance with Einstein's law of gravitation. In 1905, Einstein published the first of a series of papers supporting and extending a theory of time and space to which the name the theory of relativity had been given. These views, as expounded by Einstein, came into direct conflict with Newton's ideas of time and space, and also with Newton's law of gravitation. Since Einstein had more faith in his theory of relativity than in Newton's theory of gravitation, Einstein so changed the latter as to make it harmonize with the former. More will be said on this subject. Let not the reader misunderstand. Newton was not wholly in the wrong, he was only approximately right. With the knowledge existing in Newton's day, Newton could have done no more than he did. No mortal could have done more. But since Newton's day, physics and science in general has advanced in great strides, and Einstein can interpret present-day knowledge in the same masterful fashion that Newton could in his day. With more facts to build upon, Einstein's law of gravitation is more universal than Newton's. It really includes Newton's. But now we must turn our attention very briefly to the theory of relativity, the theory that led up to Einstein's law of gravitation. The story goes that Einstein was led to his ideas by watching a man fall from a roof. This story bears a striking similarity to Newton and the apple. Perhaps one is as true as the other. However that may be, the principle of relativity is as old as philosophical thought, for it denies the possibility of measuring absolute time or absolute space. All things are relative. We say that it takes a long time to get from New York to Albany. Long as compared to what? Long, perhaps, as compared to the time it takes to go from New York City to Brooklyn. We say the White House is large when compared to a room in an apartment, but we can just as well reverse our ideas of time and distance. The time it takes to go from New York to Albany is short, when compared to the time it takes to go from New York to San Francisco. The size of the White House is small when compared to the size of the city of Washington. Let us take another illustration. Every time the Earth turns on its axis, we mark down as a day. With this as a basis, we say that it takes a little over 365 days for the Earth to complete its revolution around the Sun, and our 365 days equal a year. But now consider some of our other planets. With our time as a basis, it takes Jupiter or Saturn 10 hours to turn on its axis. as compared to the 24 hours it takes the Earth to turn. Saturn's day is less than 1/2-hour day, and our day is more than twice Saturn's, that is. According to the calculations of the inhabitants of the Earth, Mercury completes her circuit around the Sun in 88 days, Neptune in 164 years. Mercury's year is but 1/4 ours, Neptune's 164 times ours, and observers at Mercury and Neptune would regard us from their standard of time, which differs from our standard. You may say, why not take our standard of time as the standard, and measure everything by it? But why should you? Such a selection would be quite arbitrary. It would not be based on anything absolute, but would merely depend on our velocity around the Sun. These ideas are old enough in metaphysics. Einstein's improvement of them insists not merely in speculating about them, but in giving them mathematical form. A train moves with reference to the Earth. The Earth moves with reference to the Sun. We say the Sun is stationary, and the Earth moves around the Sun. But how do we know that the Sun itself does not move with reference to some other body? How do we know that our planetary system, and the stars, and the cosmos as a whole is not in motion? There is no way of answering such a question unless we could get a point of reference which is fixed absolutely in space. We have already alluded to our view of the nature of light, known as the wave theory of light. This theory postulates the existence of an all-pervading ether in space. Light sets up wave disturbances in this ether and is thus propagated. If the ocean were the ether, the waves of the ocean would compare with the waves set up by the ether. But what is this ether? It cannot be seen. It defies weight. It permeates all space. It permeates all matter. So say the exponents of this ether. To the layman, this sounds very much like another name for the deity. To Sir Oliver Lodge, it represents the spirits of the departed. To us, of importance is the conception that this ether is absolutely stationary. Such a conception is logical if the various developments in optics and electricity are considered. But if absolutely stationary, then ether is the long sought for point of reference, the guide to determine the motion of all bodies in the universe. If there is an ether and a stationary ether, and if the Earth moves with reference to this ether, the Earth in moving must set up ether currents. Just as when a train moves, it sets up air currents. So reasoned Michelson, a young Annapolis graduate at the time, and forthwith he devised a crucial experiment, explanation of which we can simplify by the following analogy. Which is the quicker, to swim upstream a certain length, say 100 yards, and back again, or cross stream the same length and back again? The swimmer will answer that the up and down journey is longer. Our river is the ether. The Earth, if moving in this ether, will set up an ether stream, the upstream being parallel to the Earth's motion. Now suppose we send a beam of light a certain distance, up this ether stream and back, and note the time, and then turn the beam of light at right angles and send it an equal distance across the stream and back, and note the time. How will the time taken for light to travel in these two directions compare? Reasoning by analogy, the up and downstream should take longer. Michelson's results did not accord with analogy. No difference in time could be detected between the beam of light traveling up and down, and across and back. But this was contrary to all reason. If the postulate of an ether was sound, must we then revise our ideas of an ether? Perhaps after all there is no ether. But if no ether, how are we to explain the propagation of light in space and various electrical phenomena connected with it, such as the Hertzian or wireless waves? There was another alternative, one suggested by Larmor in England and Lorentz in Holland. That matter is contracted in the direction of its motion through the ether current. To say that bodies are actually shortened in the direction of their motion by an amount which increases, it's the velocity of these bodies. Approach is that of light is so revolutionary an idea that Larmor and Lorentz would hardly have adopted such a viewpoint, but for the fact that recent investigations into the nature of matter gave basis for such belief. Matter, it has been shown, is electrical in nature. The forces which hold the particles together are electrical. Lorentz showed that mathematical formulas for electrical forces could be developed which would inevitably lead to the view that material bodies contract in the direction of their motion. But this is ridiculous, you say. If I am shorter in one direction than in another, I would notice it. You would if some things were shortened and others were not. But if all things pointing in a certain direction are shortened to an equal extent, how are you going to notice it? Will you apply the yardstick that has been shortened? Will you pass judgment with the help of your eyes? But your retina has also contracted in brief. If all things contract to the same amount, it is as if there were no contraction at all. The startling ideas just outlined have opened up several new vistas, but they have left unanswered the two problems we set out to solve: whether there is an ether, and if so, what is the velocity of the earth in reference to this ether? Lorentz maintains that there is an ether, but the velocities of bodies relative to it must forever remain a mystery. As you change your position, your distances change, you change. Everything about you changes accordingly, and all basis for comparison is lost. Nature has entered into a conspiracy to keep you ignorant. Einstein starts with the assumption that there is no possible way of identifying this ether. Suppose we ignore the ether altogether. What then? If we do ignore the ether, we no longer have any absolute point of reference. For if the ether is considered stationary, the velocity of all bodies within the ether may be referred to it. Any point in space may be considered a fixed point. If, however, there is no ether, or if we are to ignore it, how are we to get the velocity of bodies in space? If we are to believe in the causal relationship between only such things as lie within the realm of observation, then observation teaches us that bodies move only relative to one another, and that the idea of absolute motion of a body in space is meaningless. Einstein, therefore, postulates that there is no such thing as absolute motion, and that all we can discuss is the relative motion of one body with respect to another. This is just as logical a deduction from Michelson's experiment as the attempt to explain Michelson's anomalous results in the light of an all-pervading ether. Consider for a moment Newton's scheme. This great pioneer pictured an absolute standard of position in space, relative to which all velocities are measured. Velocities were measured by noting the distance covered and dividing the result by the time taken. To cover the distance, space was a definite entity, and so was time. Time, said Newton, flows evenly on, independent of aught else. The Newton time and space were entirely different, in no way to be confounded. Just as Newton conceived of absolute space, so he conceived of absolute time. From the latter standard of reference, the idea of a simultaneity of events at different places arose. But now if there is no standard of reference, if the ether does not exist or does not function, if 2 points A and B cannot be referred to a third and fixed point C, how can we talk of simultaneity of events at A and B? In fact, Einstein shows that if all you can speak about is relative motion, then one event which takes, say, 1 minute on one planet would not take 1 minute on another. For consider two bodies in space, say the planets Venus and the Earth, with an observer B on Venus and another on the Earth, denotes the time taken for a ray of light to travel from B to the distance M. On the Earth has means of observing the same event. B records 1 minute. He is puzzled, for his watch records a little more than 1 minute. What is the explanation? Granting that the 2 clocks register the same time to start with, and assuming further Einstein's hypothesis that the velocity of light is independent of its source, the difference in time is due to the fact that the planet Venus moves with reference to the observer on the Earth, so that in reality does not measure the path BM and MB, but BM and MB, where BB represents the distance Venus itself has moved in the interval. And if you put yourself in B's position on Venus, the situation is exactly reversed, all of which is simply another way of saying that what is a certain time on one body in space is another time on another body in space. There is nothing definite in time. Further bewildering possibilities are clearly outlined in this apt illustration. If when you are going away on a long and continuous journey, you write home at regular intervals, you should not be surprised that with the best possible mail service, your letters will reach home at progressively longer intervals, since each letter will have a greater distance to travel than its predecessor. If you were armed with instruments to hear the home clock ticking, you would find that as your distance from home keeps on increasing, the intervals between the successive ticks, that is, its seconds grow longer, so that if you traveled with the velocity of sound, the home clock would seem to slow down to a standstill. You would never hear the next tick. Precisely the same is true if you substitute light rays for sound waves If with the naked eye or with a telescope you watch a clock moving away from you, you will find that its minute hand takes a longer time to cover its 5-minute intervals than does the chronometer in your hand. And if the clock traveled with the velocity of light, you would forever see the minute hand at precisely the same point. That which is true of the clock is, of course, also true of all time intervals which it measures, so that if you moved away from the earth with the velocity of light, everything on it would appear as still as on a painted canvas. Your time has apparently come to a standstill in one position, and is moving in another. All this seems absurd enough, but it does show that time alone has little meaning. The relativity theory requires that we thoroughly reorganize our method of measuring time, but this is intimately associated with our method of measuring space, the distance between two points. As we proceed, we find that space without time has little meaning, and vice versa. This leads Minkowski to the conclusion that time by itself and space by itself are mere shadows. They are only two aspects of a single and indivisible manner of coordinating the facts of the physical world. Einstein incorporated this time-space idea in his theory of relativity. How we measure a point in space. Suppose I say to you that the chemical laboratory of Columbia University faces Broadway. Would that locate the laboratory? Hardly, for any building along Broadway would face Broadway. But suppose I add that it is situated at Broadway and 117th Street, southeast. There could be little doubt then. But if, further, this laboratory would occupy but part of the building, say the third floor, then the situation would be specified by naming Broadway, 117th Street SE, third floor. If Broadway represents length, 117th Street width, and third floor height, we can see what is meant when we say that 3 dimensions are required to locate a position in space. A point on a line may be located by 1 dimension. A point on a wall requires 2 dimensions. A point in the room, like the chemical laboratory above ground, needs 3. The layman cannot grasp the meaning of a 4th dimension, yet the mathematician does imagine it and plays with it in mathematical terms. Minkowski and Einstein picture time as the 4th dimension. To them, time occupies no more important position than length, breadth, or thickness, and is as intimately related to these 3 as the 3 are to one another. H.G. Wells, the novelist, has beautifully caught this spirit when in his novel, The Time Machine, he makes his hero travel backwards and forwards long time just as a man might go north or south. When a man with his time machine goes forward, he is in the future. When he goes backwards, he is in the past. In reality, if we stop to think a minute, there is no valid reason for the non-existence of a 4th dimension. If 1, 2, and 3 dimensions, why not 4 and 5 and 6, for that matter? Theoretically, at least, there is no reason why the limit should be set at 3. However, our minds become sluggish when we attempt to picture dimensions beyond 3, just as an extraordinary effort on our part is needed to follow Einstein when he juggles with space and time. Our difficulty in imagining for dimensions may be likened to the difficulty two-dimension beings would experience in imagining us, beings of the conventional three dimensions. Suppose these two-dimensional beings were living on the surface of the earth, what could they see? They could see nothing below and nothing above the surface. They would see shifting surfaces as we walked about, but being sensitive to length and breadth only, and not to height, they could gain no notion whatsoever of what we really look like. It is thus with us when we attempt to picture four-dimensional space. Perhaps the analogy of the motion picture may help us somewhat. As everybody knows, these motion pictures consist of a series of photographs which are shown in rapid succession on the screen. Each photograph by itself conveys a sensation of space that is, of three dimensions, but one photograph rapidly following another conveys the sensation of space and time. For dimensions, space and time are interlinked. The time-space idea further developed. We have already alluded to the fact that objects in space moving with different velocities build up different time intervals. Thus, the velocity of the star Arcturus, if compared with reference to the Earth, moves at the rate of 200 miles a second. Its motion through space is different from ours, objects which, according to Lorentz, contract in the direction their motion to an extent proportional to their velocity, will contract differently on the surface of Arcturus than on the Earth. Our space is not Arcturus' space, neither is Arcturus time our time. And what is true of the discrepancies existing between the space and time conceptions of the Earth and Arcturus is true of any other to bodies in space moving at different velocities. But is there no relationship existing between the space and time of one body in the universe as compared to the space and time of another? Can we not find something which holds good for all bodies in the universe? We can express it mathematically. It is the concept of time and space interlinked, of time as the fourth dimension, length, breadth, and thickness being the other three, of time as one of her coordinates, and at right angles to the other three, a situation which requires a terrific stretch of the imagination to visualize. The four dimensions are sufficient to coordinate the time-space relationships of all bodies in the cosmos, and hence have a universality which is totally lacking when time and space are used independently of one another. The four components of our time-space are up and down, right and left, backwards and forwards, and sooner and later. Strain and distortion in space. The four-dimensional unit has been given the name world line, for the world line of any particle in space is in reality a complete history of that particle as it moves about in space. Particles, we know, attract one another. If each particle is represented by a world line, these world lines will be deflected from their course owing to such attraction. Imagine a bladder representing the universe, with lines on it representing world lines. now squeeze the bladder. The world lines are bent in various directions. They are distorted. This illustrates the influence of gravity on these world lines. It is the strain brought about due to the force of attraction. The distorted bladder illustrates even more, for it is a true representation of the real world. In our conventional language, we speak of the sun as exerting a force on the earth. We have seen, however, that this force brings about a distortion or strain in world lines, or what amounts to the same thing, a distortion or a strain of time and space. The sun's force, the force of any body in space, is the force due to gravity, and these forces may now be treated in terms of the laws of time and space. The Earth, Professor Eddington tells us, moves in a curved orbit, not because the sun exerts any direct pull, but because the Earth is trying to find the shortest way through a space and time, which have been tangled up by an influence radiating from the sun. At this point, Newton's conceptions fail, for his views and his laws do not include strains in space. Newton's law of gravitation must be supplanted by one which does include such distortions. It is Einstein's great glory to have supplied us with this new law. Einstein's law of gravitation. This appears to be the only law which meets all requirements. It includes Newton's law and cannot be distinguished from it. If our experiments are confined to the Earth and deal with relatively small velocities, but when we betake ourselves to some orbits in space with a gravitational pull much greater than the Earth's, and when we deal with velocities comparable to that of light, the differences become marked. In the beginning of this chapter, we referred to the elaborate eclipse expedition sent by the British to test the validity of Einstein's new theory of gravitation. The British scientists would hardly have expended so much time and energy on this theory of Einstein's, but for the fact that Einstein had already scored one great victory. What was it? Imagine but a single planet revolving about the sun. According to Newton's law of gravitation, the planet's path would be that of an ellipse, that is, overland the planet would travel indefinitely along this path. According to Einstein, the path would also be elliptical, but before a revolution would be quite completed, the planet would start along a slightly advanced line, forming a new ellipse slightly in advance of the first. The elliptic orbit slowly turns in the direction in which the planet is moving. After many years, centuries, the orbit will be in a different direction. The rapidity of the orbit's change of direction depends on the velocity of the planet. Mercury, moving at the rate of 30 miles a second, is the fastest among the planets. It has the further advantage over Venus, or the Earth, in that its orbit, as we have said, is an ellipse, whereas the orbits of Venus and the Earth are nearly circular. And how are you going to tell in which direction a circle is pointing? Observation tells us that the orbit of Mercury is advancing at the rate of 570 seconds of arc per century. We can calculate how much of this is due to the gravitational influence of other planets. It amounts to 530 seconds per century. What are the remaining 42 seconds? You might be inclined to attribute this shortcoming to experimental error, But when all such possibilities are allowed for, our mathematicians assure us that the discrepancy is 30 times greater than any possible experimental error. This discrepancy between theory and observation remains one of the great puzzles in astronomy until Einstein cleared up the mystery. According to Einstein's theory, the mathematics of the situation is simply this. In one revolution of the planet, the orbit will advance by a fraction of a revolution equal to 3 times the square of the ratio of the velocity of the planet to the velocity of light. When we allow mathematicians to work this out, we get the figure 43, which is certainly close enough to 42 to be called identical with it. Still another victory. Einstein's third prediction, the shifting of spectral lines toward the red end of the spectrum, in the case of light coming to us from the stars of appreciable mass, seems to have been confirmed recently, March 1920. The young physicist Ten Bond writes, Professor Einstein to a friend, have now as good as certainty so get why Sicker proved the red displacement of the spectral lines, and have cleared up the grounds of a previous disappointment. Velocity or movement in space is at the basis of Einstein's work as it was at the basis of Newton's, but time and space no longer have the distinct meanings that they had when examined with the help of Newton's equations. Time and space are not independent, but interdependent. They are meaningless when treated as separate entities, giving results which may hold for one body in the universe, but do not hold for any other body. To get general laws which are applicable to the cosmos as a whole, the fundamentals of mechanics must be united. Einstein's great achievement consists in applying this revised conception of space and time to elucidate cosmical problems. World lines representing the progress of particles in space, consisting of space-time combinations of 4 dimensions, are strained or distorted in space due to the attraction that bodies exhibit for one another, the force of gravitation. On the other hand, gravitation itself more universal than anything else in the universe may be interpreted in terms of strains on world lines, or what amounts to the same thing, strains of space-time combinations. This brings gravitation within the field of Einstein's conception of time and space. That Einstein's conception of the universe is an improvement upon that of Newton's is evidenced by the fact that Einstein's law explains all that Newton's law does, and also other facts which Newton's law is incapable of explaining. Among these may be mentioned the distortion of the oval orbits of planets round the Sun, confirmed in the case of the planet Mercury, and the deviation of light rays in a gravitational field, confirmed by the English solar eclipse expedition. Einstein's theories, supported as they are by very convincing experiments, will probably profoundly influence philosophic and perhaps religious thought, but they can hardly be said to be of immediate consequence to the man in the street. As I have said elsewhere, Einstein's theories are not going to add 1 bushel of wheat to war-torn and devastated Europe, but in their conception of a cosmos decidedly at variance, with anything yet conceived by any school of philosophy. They will attract the universal attention of thinking men. In all countries, the scientist is immediately struck by the way Einstein has utilized the various achievements in physics and mathematics to build up a coordinated system showing connecting links where heretofore none were perceived. The philosopher is equally fascinated with the theory which, in detail extremely complex, shows a singular beauty of unity in design when viewed as a whole. The revolutionary ideas propounded regarding time and space, the brilliant way in which the most universal property of matter, gravitation, is for the first time linked up with other properties of matter, and, above all, the experimental confirmation of several of his more startling predictions always, the finest test of scientific merit stamps. Einstein is one of those supermen who from time to time are sent to us to give us a peep into the beyond. Albert Einstein was born in Germany some 45 years ago. At first he was engaged at the Patent Bureau in Bern, and later became professor at the Zurich Polytechnic. After a short stay at Prague University, he accepted one of those tempting academic professorships at the University of Berlin, professorships which ensure a comfortable income to the recipient of one of them. Little university work beyond, perhaps, one lecture a week, and splendid facilities for research. A similar inducement enticed the chemical philosopher Van T. Hoff to leave his Amsterdam, and the Swedes came perilously near losing their most illustrious scientist, Arrhenius. Einstein published his first paper on relativity in 1905, when not more than 30 years old. Of this paper Planck, the Nobel laureate in physics this year, has offered this opinion. It surpasses in boldness everything previously suggested in speculative natural philosophy, and even in the philosophical theories of knowledge. The revolution introduced into the physical conceptions of the world is only to be compared in extent and depth with that brought about by the introduction of the Copernican system of the universe. Einstein published a full exposition of the relativity theory in 1916. During the momentous years of 1914 to 19, Einstein quietly pursued his labors. There seems to be some foundation for the belief that the ways of the German High Command found little favor in his eyes. At any rate, he was not one of the 40 professors who signed the famous manifesto extolling Germany's aims. We know for a fact, writes Dr. O.A. Rankine of the Imperial College of Science and Technology, London, that Einstein never was employed on war work. Whatever may have been Germany's mistakes in other directions, she left her men of science severely alone. In fact, they were encouraged to continue in their normal occupations. Einstein undoubtedly received a large measure of support from the imperial government, even when the German armies were being driven back across Belgium. Quite recently, June 1920, the Barnard Medal of Columbia University was conferred on him in recognition of his highly original and fruitful development of the fundamental concepts of physics through application of mathematics. in acknowledging the honor. Professor Einstein wrote to President Butler that, quite apart from the personal satisfaction, I believe I may regard your decision to confer the medal upon him as a harbinger of a better time, in which a sense of international solidarity will once more unite scholars of the various countries. Thanks a million for being part of today's show. Your presence makes it all worthwhile. Wishing you a fantastic day until we meet again. Stay awesome.